Hey guys, my name is Trevor Sullivan and welcome back to my video channel. Thank you so much for joining me for yet another video in our Rust programming tutorial video series. Let's talk about a new topic today. We're still going to be continuing on with Rust threading, but this is going to be a slight deviation from the last couple of topics. First of all, we introduced the basics of Rust threading, then we talked about how scoped threading works, and then we talked about how to share data across different threads by using a mutex. So we're going to be taking a look at a slightly different mechanism of passing data between different threads. And this doesn't require that you use threads. You can actually use this technique within just a single thread in your main thread of your Rust application, but you do have the ability to build a multi-threaded application in Rust by using this concept known as message passing. So, the first thing I'm going to point you to, if you'd like to read more about this topic, is the Rust programming language book. You can just search for that on your favorite search engine. And then over under the chapter 16, subsection 2, there's an article that talks about using this message passing concept so that you can send messages and receive messages from a thread in your Rust program. And this is a very safe way for you to pass data between threads. So let's say, for example, that you'd like to send some work off to a worker thread, but you want your main function to go off and do some different work entirely. Well, what you can essentially do with message passing is you can queue up a bunch of messages, a bunch of work that you want your worker threads to process. To give you a little bit of an analogy, I used to work back in my mid-teen years. I worked at a restaurant, and during really busy times at the restaurant, the working staff in the front as well as in the back kitchen area were extremely busy, and there was nobody assigned to dishwashing. Dishwashing during rush periods, like lunch and dinner rush periods, was always something that was kind of put off until after the rush died down a little bit and some of the worker resources freed up to go and work on cleaning the dishes, right? So, what would happen in the meantime? Well, we're creating lots of dirty dishes during those peak periods. So, what would happen is that the front and back end staff would end up taking dirty dishes, they would put them on the wash area, they would queue them up to be washed, but since nobody was there actually washing the dishes, there would be just a huge pile of dishes a little bit later on for somebody to ultimately wash. And so you can kind of think of message passing as the same type of concept where you have the ability to queue up messages without necessarily processing them in real time. And then at some point down the road, your worker process or your thread in your Rust program can start pulling messages off of that queue, processing them, and then moving on with its life. Just kind of rinse and repeat, right? So we have this concept called message passing, and there's a couple of different types of message queues that we can use. There's an asynchronous message queue and a synchronous message queue, and each of them work a little bit differently. Now, this is still going to be part of the sync module in the standard crate for Rust. So if you recall back when we were talking about the mutex structure that allows us to lock access to a particular variable in memory, that's also part of this sync module. So we're going to be kind of staying in that same arena of functionality, but the sync module actually has its own child module called MPSC. And if you're not really clear on what MPSC stands for, it stands for Multiple Producer Single Consumer. So the important concept to understand with these message passing channels is that you can only have one thread that is receiving messages from one of these message channels at any given point in time. However, you can have many different handles that are producing or sending messages or queuing up work inside of that channel. So we're going to take a look at how you can actually have multiple instances of a sender or producer and how you can use the receiver, the singular receiver, in order to pull messages off that queue and process them, whatever processing it means to you. It could be inserting them into a database. It could be, transforming the data and sending it off to some other API. But we're just going to keep things really simple so that you understand the fundamentals of these channels. So essentially, the way that we use these channels, it's actually very, very simple. So don't get overwhelmed by this. Basically, we just instantiate a channel using this channel function that's exported by the MPSC child module. And then we get a tuple value returned. So we can destructure the tuple value into two different variables here. So we have maybe a TX and an RX value, and you can call those variables whatever you want to. You could use sender or transmitter and receiver or something like that if you wanted to. You can name those variables whatever you want to, but basically this destructuring here is just taking the two tuple values that we get back from the channel, and it assigns the first one to whatever this first variable name is, and then the second variable receives the second value from that return value. And then what we can do is use the transmitter's send method here in order to send data into the channel. Then we can use this RX variable here to receive messages from the channel. And again, you can do all of this in a single thread. So we don't have to use threads to use this message passing functionality, but generally speaking, you're probably going to be having a multi-threaded application if you are queuing up work and then pulling work off of these types of message queues. So we're going to go ahead and spin up an example of this, but before we actually jump into the code, make sure that you head over to my YouTube channel, which you're probably on right now if you're viewing this, youtube.com/Trevor Sullivan. I'm an independent content creator, so any kind of support that you can provide to me is incredibly helpful to me so that I can continue bringing you more videos like this one and the entire Rust programming tutorial series that we have in this playlist right here. So make sure that you are tracking this Rust programming tutorial playlist. It really helps if you leave a like on each video that you watch. If you learned anything new from that video, leave a thumbs up on it. And also just leave a comment on the video and let me know what you thought of that video. And let me know what other kind of Rust programming topics you'd like to see on my channel. Also, there's an interesting community tab here where I can post updates very similar to Twitter and LinkedIn and that kind of thing, which you can also follow me on. But sometimes I post little quiz questions here, and you can use that knowledge to help kind of test yourself to see if you understand those fundamental concepts or if there's certain topics that you need to do a little bit more studying on. And I generally try to tailor those quiz questions to the topics that I have videos covering. So you can always go back and see a video that covers the topic that pertains to the question. So let's head over to the Rust documentation here. We're in the standard crate documentation. And then if we go to child modules down here, we should see our sync child module. And then within sync, if we go down to modules, we've got this MPSC module. And this is what contains all of the capabilities of the synchronous and asynchronous channels. So if we head down to functions here, it's actually pretty straightforward because there's only two different functions that are exported from this MPSC module here. We have the channel, which will create by default, an asynchronous channel here. It gives you the sender and the receiver variables so that you can use those to send and receive messages. But you also have a sync channel function, and this allows you to create a synchronous channel. And one of the key differences that you'll notice between async and sync channels is that the sync channels actually have the ability to assign a limit on the number of items that can appear within this channel. So when you initialize a synchronous channel, you actually have to specify a boundary size, and that boundary size is actually the internal buffer. And if that buffer fills up, you won't be able to send any more data into the channel, or what I like to think of as a message queue. So let's go ahead and start out by instantiating one of these asynchronous channels. It'll give us this tuple pair with our sender and our receiver. You will also notice that it uses generic types here. So the channel type can actually work with, integer values, with floating point values, with string values, custom data structures that you define in your Rust application. So it gives you a lot of flexibility because it is all built around generics. And we'll take a look at how to specify which generic type you want to use for your specific channels. All right, so let's go ahead and add some code into our sample project here. So as I've been doing in previous videos, we're just going to go into the root of our project and create a file. And I'll call this my mpsc.rs. I always like to prefix it with my or test or something like that to make sure that I don't accidentally conflict with the built-in module type names. So what we're going to do in here is say pub fn test message channels, or maybe just test channels for starters here. And inside this function body, we'll go ahead and create our channel. And then over in main.rs here, we'll comment out the call to mutexes, and we'll add in a reference to pub mod my MPSC. And down here at the end of main, we'll do MPSC, my MPSC, and call test channels. All right, so now that we've got that call there, let's go ahead and come back to our function, and we'll implement some code for this function. So the first thing that we're going to do is to instantiate a channel. And the way that we do that is by using the module for starters. So let's do use standard and then sync and then the MPSC module. And then once we've imported the MPSC module, we should have access to the channel and sync channel functions down here that we can use to instantiate the channels. So for starters, we'll just work with the async channel right here. So we'll do let tx and rx equal, and let's wrap that in parentheses there. And then we're going to call MPSC channel. And this doesn't take any input parameters. So when you create an asynchronous channel, there are no input arguments to worry about here. And with the synchronous channels, you do have to make sure that you specify what the buffer size, the number of items inside of the queue that are going to be supported. But the asynchronous channels have kind of an unlimited buffer, so to speak, based on, of course, how much system memory you have. And then you can also see that we need to specify what our generic type is going to be. One way that we could do that is to specify on the left-hand side what our tuple pair is going to look like. So we could do something like, sender and then U8 and then receiver U8 or something like that if we want our underlying data type to be that. But then over here, what we could also do is specify a double colon here and then specify our less than greater than signs with the data type that we want to use inside of that. And then the compiler can infer on the left-hand side the data types of each of our variables right here. So now that we've got the generic data type declared for this channel, let's start to put some messages on the channel. We're not going to introduce threads for now. We're just going to use our main thread. We're just going to put some messages on the channel, and then we're going to pull those messages off the channel by receiving them. So for starters, we need to use the transmitter, the TX right here, and I'll just call this transmitter just to make it a little bit more clear, and call this receiver. And so what we do is we say transmitter dot, and then you can see right down here, we've got this send function. And all we have to do is specify the data that we want to feed into the message queue or channel. So in this case, I can use any unsigned 8-bit integer value. So anything from 0 to, I want to say 255. So let's try maybe just 100 and save that. And then I'll just do Alt-Shift down arrow to copy that. And let's add a value of 152. So as you can see, that works just fine. We are not obliged to pull messages off of the channel. We can literally just send data into the channel and let our program exit, and that memory will get cleaned up by Rust after our program exits. So let's just do a cargo run here and see what we get back. Looks like we're having a little bit of an issue here with the my mutex file. So let me go clean that up really quickly here. Let's go to my mutex and see what's going on here. So I have a incomplete line right there. So let's clean that up and do cargo run. All right, so as you can see, the program does work perfectly fine. We put 2 messages onto the queue, but we never actually receive them, right? Also, when you send a message into the queue, you get this result object that wraps the either successful or failure status of the send operation. So if we say let send result equal the result of the send, we get this result. It gives us a unit type or a send error that wraps the underlying data type that we are trying to send into the channel, which in this case is an unsigned 8-bit integer. And that way we can check to see if the send was or wasn't successful. So let's just print the status and say print line send status, and then we'll just pass in send result dot is okay. and that'll just give us a Boolean type indicating whether or not the send was successful. So we should see true there if the send was successful. And sure enough, we get send status is true because there is no reason why that shouldn't have succeeded. Now, one important thing to note about channels is that if the sender or receiver were to close, then that would cause the entire channel to close, and sending or receiving, if there was still an open handle to either of those, would actually fail. So one thing that we can do to kind of demonstrate that is to just drop the receiver manually before we attempt to send. And then if we try to run this program again, you can see that the send status is now false instead of true because the send actually failed. And why did the send fail? Well, it failed because the receiver was closed, and either if the receiver or the sender is closed off, then that entire channel is now rendered invalid. So make sure that if you are dropping your receiver, that you are checking the status of your send result to make sure that the sender is successful and vice versa. All right, so we are sending a couple of messages onto the queue. That's working perfectly fine. Let's go ahead and take our receiver, which is in the receiver variable, and we'll call the receive function, recv. Now there's two different variations that we have. One is recv_timeout, and this accepts a duration as input. So what you can do is either call just recv, which is kind of the simplest form. It doesn't take any input arguments, but it will cause your thread to block until a message is available. So if there's no data on the channel and you try to call a receive operation, then your thread is going to completely hang, and there's not really any way to recover it except to terminate the thread and perhaps start up a new one. Now, if you want to do a non-blocking operation that allows you to check for a message, but if there's no messages, then you can continue doing some other work. Maybe you're processing multiple channels from a single thread and you need to have that capability. So then what you can do is do receive timeout. That's what accepts a duration. You could set a duration of something like 300 milliseconds so that it very quickly times out if there's no message on the channel for it to receive. And then that will allow your thread to continue executing and doing some other productive work while it waits for this channel to have some data on it. So let's just call receive for now. And what I'm actually going to do is put the receive way up here before we put messages on the queue. And if I run this, what you're going to see is that my program completely hangs, because if we try to receive a message and we haven't yet put a message onto the channel, then we simply are going to block indefinitely. But if we cancel this and then we use receive_timeout and specify a duration here, if you watched my earlier video, it was like 4 or 5 videos ago on time and chrono crates, then you'll probably be familiar with this, but we'll do use standard time duration. And then what we can do is just pass in duration from milliseconds and say, just wait for 300 milliseconds to see if there's a message. And as you can see, it says, all right, there's no message on the queue, so I'm just going to terminate, and we're going to move on with the next line of execution, and everything is healthy, right? Our send status is still successful because our receiver hasn't closed. We just tried to get a message off the channel and we're unsuccessful. But if somebody does put a message on that queue, we can always come back with the receiver and then try again. So what we can do down here is say, all right, put a couple of messages onto the channel, and then we'll try to receive a second time after that, and it should work. And so what we'll do is say, let receive result equal that, and then we'll do print line and say receive result is, and just do receive result dot is okay, because the receive result here is again wrapped in a result object that has the U8 value that was passed into the channel, or if an error occurs, we get the timeout error right over here. So we'll just do a Boolean check for is okay, and we should receive true if it's healthy. And sure enough, sending is still healthy, receiving messages is still healthy as well, so we're able to pull messages off of that channel. All right, so all of that seems to be working okay. And what if we wanted to get the actual value, right? Well, what if we want to get the value of this receive result? Well, what we can do is simply unwrap the result from ReceiveResult, and we should get whatever was put onto the channel here. So as you can see, the first message that came off the channel is 100, and that's right up here on line number 10. We put 100 onto the channel. And then the second, if we were to try to run this code a second time, let's go ahead and try that again. So now we get 100, and then the second time that we run the receive operation, we get 152. So now what we can do is to take things a little bit further. We've seen how the underlying APIs actually work for the channel with the sender and the receiver, and what happens if you drop the receiver before you actually try to send any data. And now what we can do is actually create a separate thread that just has the receiver, right? And then we can pass off the receiving operation to that thread. And from the main thread, we can just focus on sending data to the channel. It doesn't really matter if the main thread is doing the sending or the receiving. You could always spin up a thread that puts messages into the channel, and the main thread could receive the messages off the channel. It's really up to you how you want to go about implementing that, but you can go either direction because the main thread is just another thread in your Rust program. There's not anything particularly special about the main thread except that it's your primary entry point into your application. So what we're going to do is just rip out this receiving here, and we're going to implement a closure or anonymous function, which I also have a separate video on in my Rust programming tutorial playlist. So what we're going to do is create an anonymous function and say, let's receive a message. So we'll say receiver dot receive timeout, and we'll say 300 milliseconds. Of course, we have to do a duration here. We'll say from 300 milliseconds, and let's try to get the result. So we'll say receive result equals that. And then we want to assign this closure to a variable as well, because we need to be able to pass the closure into the thread spawn operation so we can kick off the thread from main. So let's do let processor code equal this closure. We'll terminate it with a semicolon right there. And then the other thing I'm going to do here is actually wrap everything in a loop. So I'm just going to do kind of this infinite looping operation where we attempt to receive a message, and if it fails, it'll just kind of loop again and continue attempting. So what we'll do is do a print line statement here just to give us some feedback in the terminal to show that the child thread is actually starting up. So we'll say starting processor thread, and we'll actually put that right before the loop because we only want that to print once. But every single iteration of the loop, we want to see some feedback that it's attempting to receive a message off of the channel. So what we'll do is say print line attempting to receive message from channel, ... And so now we're going to attempt to receive the result here. And if the result is okay, like we saw before, then we'll go ahead and print out the value from the result. So we'll say if receive result dot is okay, then in our block here, we are going to say print line received message. We'll put a placeholder in there with the curly braces right here. And then we'll pass in as a substitute for that, we'll pass in receive result dot unwrap, and that should give us our underlying value. I'm also going to bump out the timeout just a little bit so we're not hammering it too quickly. So I'll just set it to like 800 milliseconds just to give us a little bit more spacing between each attempt so we don't fill up our terminal logs while we're trying to work with it here. So what we're going to do now is customize our input code a little bit. So what we're going to do is rip out the sending here. After we kick off the processor, I'm going to write some code with a for loop here that just says for x in range from 1 to 6, 1 to equals 6. Then we're going to send a message into the channel. So let's do let send result equal transmitter.send, and then we'll just send in x, whatever x is. So it'll start at 1, 2, 3, 4, 5, and then 6. And I'll remove that duplicate line right there because we don't need that. And So now we should be able to iterate over this and send a bunch of messages in there. And then we want to make sure that we wait for our worker thread to exit or something like that, right? So what we'll do is spawn our worker thread using standard thread spawn. And we're just going to kick off processor code, which is our anonymous function containing our thread. Now you can see that we have this message here that says that the receiver cannot be shared between threads safely. And if you watched my earlier videos on threading and scoped threads, you'll probably know that in order to solve this, we actually need to move ownership of the receiver that we're referencing right here on line number 14. This receiver is currently owned by the outer scope here. And so what we need to do is use the move keyword on the closure to actually move ownership of the receiver variable that's owned by the test channel's scope, and then move ownership into the closure so that the closure can have exclusive control over that receiver and the main thread will not be able to access it anymore. All right, so let's go ahead and give this a try. I'm also going to do a dot join here to make sure that our main thread blocks until the child thread is finished. And at the moment, we don't have any criteria in here to actually exit the child worker thread, the processor code thread here. So it's actually going to keep our program running infinitely, but let's just take a look here. All right, so as you can see very quickly here, we were able to send the numbers 1 through 6, and the child thread actually received all of those messages. But just to slow things down a little bit, I'm actually going to do a thread sleep in our for loop right here. So we'll just do standard thread sleep, and we'll specify a duration from milliseconds of about maybe 200 milliseconds. And let's see what happens now. All right, so still goes pretty quickly right here because our receive timeout interval up here is set to 800. So we're sending a whole bunch of messages in a short period of time. I'm actually going to bump down that threshold right here to, let's say, 200 milliseconds as well. And hopefully we see something a little bit more interesting. All right, well, it's still running pretty quickly here, but you kind of get the idea. Basically, our outer thread, our main thread, is running this for loop. We're putting each of these numbers into the channel, and then our processor right here is receiving all of those. And one thing that we could do to handle some exit criteria is to set a certain failed count. So if we fail to receive a message maybe 10 times in a row, then we want to go ahead and abort the processor thread because there doesn't seem to be any work coming in. So we can track that inside of the child thread. We'll say let failed count equal 0 U8. And then on each iteration here, we'll just say if the result is not okay, so if we're not able to get a message, so else, then we'll go ahead and increment the failed count. So we'll say failed count plus equals 1, and we need to make that variable mutable as well. Otherwise, we'll get this error down here about it not being mutable. And then we'll say that if the failed count is greater than 10, then we're going to go ahead and just abort operations because we're obviously not getting any work. So we'll say print line aborting processor thread no work available. And then we'll simply use the break statement here to break out of the parent loop right here. And then that'll cause the entire closure to return. And then control should be given back to our main thread. Our main thread doesn't have any more work to do after spawning the thread either. So our program should exit somewhat gracefully after we run everything. So there we go. We're sending some messages into the queue. We receive all of them. And after 10 attempts failed to receive any messages, it just aborts the processor thread, and then our main thread exits, and our program has returned control back to our terminal. So of course, you're welcome to create additional producers as well. So one of the things that you can do is, since it's called multiple producer single consumer, we already have a single consumer right here, which is our processor code closure. But if we wanted to, we could actually take this transmitter and clone the transmitter so that we have two different transmitter handles. And then we could actually create additional threads, pass in each of those separate handles to each of the producer threads, and those additional threads could then put more messages onto the channel so that our processor thread right here can continue to process them. Also, if you need to create multiple channels, you're welcome to do that as well. You can create channels with different types beyond just an unsigned 8-bit integer. This is a really convenient way to just kind of demonstrate the concept. But again, in most use cases, you're probably going to be using at the bare minimum, string data or custom data structures or things of that nature. So kind of let your imaginations flow. Make sure that you play around with this code and really understand how channels work. And then you'll be fully equipped to use multi-threading in your Rust applications to improve performance and really squeeze out the power of your server processors or desktop workstation processors that you're running your applications on. So that's pretty much everything I had for this video. I hope you guys enjoyed the topic. Again, please leave a like, subscribe to the channel. That really helps me out. And then just leave a comment and let me know what you thought of this video. Let me know what you learned from this video and what other topics on Rust you would like to see in the future. Thanks for watching, and we'll see you soon.